Alrighty, lads and ladies, welcome back to Calc 2. I apologize for the loss of class on Wednesday. That is no fun. But today we will continue where we left off on Monday. So on Monday, we worked to develop some basic results on infinite series. Today we're going to move forwards talking about a few more theorems about infinite series. And I will also show you a technique for a special class of series called telescoping series. So let's go ahead and get into it. The other thing I want to talk about today, and if I don't do this before the end of class, remind me, is the test, exam 2. Oh. So this, of course, is MAC2312, section number is 004, which is a Calc 2 class. And the date today is the 25th of February, 2022. Today, we're going to finish section 11.2 on the sort of intro to series. So I mentioned this, but from 11.2 through 11.11, that whole 9-section stretch of the textbook is about infinite series. So this is not a topic that's going away anytime soon, and we're going to be developing more and more and more results about series over the next few weeks, not just up to exam 2, but indeed up through a good chunk of the exam 3 material will also be infinite series stuff. So make sure you're taking this seriously as you work the problems. Make sure you are internalizing the notation, not BSing it at all. It's very, very important. Last time, we defined the infinite series S equals sigma n from 0 or wherever to infinity of an as the limit of partial sums from capital N to infinity S sub n, right? S sub capital N. I mentioned that your textbook uses a lowercase n here, which is a terrible choice of notation because it makes it impossible to write this, which is the sort of natural way of understanding this infinite series. The full infinite series is the limit of this kind of finite series, very much in the same way that the similar to how we wrote the integral from 0 to infinity of f of x dx as the limit as r goes to infinity of the integral from 0 to r of f of x dx. Right, and we said that the infinite series converges if this limit exists and is finite, right? If the limit of the partial sums exists and is finite. Now, your first few homework problems have you just writing out the first few partial sums for an infinite series and conjecturing as to whether or not you think that that limit of partial sums exists and is finite, trying to guess at the sum of the series. What I want to do today is develop our first few kind of formal results. Those will be done in a few different ways. The first one is this theorem called the test for divergence, which is maybe a bit of a misnomer because this will not always detect if a series diverges, but it has the ability to, in certain cases, detect whether a series diverges. And I'll abbreviate this as TFD because we're going to write it somewhat often. What this says is if the limit as n goes to infinity of the an is anything other than 0, then the series sigma n from 0 or wherever to infinity of an must diverge. And to give you an idea for why this is true, I'm going to sketch a bit of a proof here. We're not going to go through the full proof, but I do want you to understand why this is true. And I hope that it will help you avoid misusing the theorem, because this is an often misused result. This is our first sort of convergence test, and we will have many, many more of them. I would recommend doing something like flashcards or having a special place in your notes where you put all the convergence tests for series, because you need to remember their name, you need to remember their hypotheses, and you need to remember their conclusions. And they need to be remembered precisely, like exactly as they are stated, more or less word for word. So a proof sketch. Suppose that the limit as n goes to infinity of an is equal to L, and that's not 0. So what I'm going to do then is show that the series sigma an has to diverge, right? That's what this theorem says. It says if the limit is not 0, then the series has to diverge. The limit is not equal to the series. I want to make that abundantly clear, right? The limit of the an is not sigma an. This thing, sigma, very, very different from a limit. So please never write sigma an equals lim an. I'll repeat that. But we're assuming that this limit comes out to some number L, which is not 0. And I want to convince you that under those conditions, this series must diverge. Well, if I tell you that the limit as n goes to infinity of an is equal to L, then for large values of n, what does it mean to say the limit of the ans is equal to L? It means that the ans themselves, as n gets bigger and bigger and bigger, get closer and closer and closer to L, right? That was what we learned when we talked about limits of sequences. The an here on its own without the sigma, that's a sequence. This is a series. The an, the thing inside, is a sequence. So if the limit of an is L, then we know that for large values of n, I already wrote that, we know that an is approximately equal to L. Right? If you put a really, really big value in for n, then the an itself should be very close to L. That's exactly what it means to say this limit is equal to L. So the series sigma n from 0 to infinity of an, which is like a0 plus a1 plus a2 plus on, plus like, say, a sub capital N, and then an plus 1, and a capital N plus 2, and on and on. These first few terms could be whatever, but all of these later terms are approximately equal to L. So this would be like a0 plus a1 plus a2 plus, say, everything after capital N is approximately equal to L. So it's like plus L plus L plus L. No. This part of the series, the part that we call the tail, is like L times infinity. So it doesn't matter what this is. There's only finitely many terms here. This thing is definitely finite. So you have something finite plus L times infinity. Well, shit, that's gotta be infinity. So if the series comes out to infinity, right, that means the series diverges. Series diverges. So the thing that should be going on in your mind when you think about the test for divergence is that if the things you're adding up don't get small, right? If the things you're adding up, which are the ANs, do not get very, very close to 0 as n gets very, very big, then basically you're adding up a bunch of not very, very small things. And if you take a bunch of things that are not very, very close to 0 and you add them all up, you're going to get something really big. Like the series 1 plus 1 plus 1 plus 1 plus 1, on and on and on for infinity. That's definitely going to diverge, right? You've got 1 plus itself infinitely many times. If you replace that 1 by any other number L besides 0, then your series is basically going to be L plus L plus L plus L plus L, on and on and on forever. And no matter what L is, if it's anything other than 0, then this piece is going to be infinite. That's the basic idea behind the test for divergence. And before we go and do an example with this, I want to give you a stern and solid warning. The converse is false. In other words, it is not true that just because the limit as n goes to infinity of an is 0, that sigma n from 0 or wherever to infinity of an converges. There are many, many series where the limit of the an is 0, and that series still diverges. So in other words, the test for divergence, the word here is converges. In other words, the test for divergence says if the limit of the an is not 0, then the series sigma an diverges. If the limit of the an is 0, then the test is inconclusive. Warning, the converse. Yeah, that word is converse, like the shoes. Converse, meaning the logical, what you get if you flip the implication around. So if lim an is not 0, the series diverges. It's not true that if the lim an is 0, the series converges. And this is how I would encourage you to think of TFE. This theorem here. This will avoid a common pitfall. And I have no problem telling you this one of the true-false questions on your next test is going to be true or false. If the limit as n goes to infinity of an equals 0, then the series sigma an converges. And the answer to that question is false. There are many, many series where the limit of the an is 0, but the series sigma an diverges. And I'll show you such an example today. Before I do that, let's work an example just using this theorem. Let's investigate the convergence of the series S equals sigma n from 1 to infinity 2n squared plus 3 over 5n squared minus 1. If we wanted to, we could write out the first few terms of this series. We could try to find the first few partial sums and ask ourselves, are those partial sums getting closer and closer to something? But this is a good sort of first example of what we're going to do most of the time with infinite series, where instead of working directly with the series, we're going to go ahead and do something with the ANs on their own to infer something about the series. And specifically, I'm going to apply this theorem. So here's how you do this. You tell your reader what test you're going to use. Right? Always. We're going to have many, many tests. You tell your reader what test you're going to use. I'm going to use TFD, the test for divergence. Then you write down, in general terms, the object of the test without plugging anything in. The limit of the ANs is the limit as n goes to infinity of 2n squared plus 3 over 5n squared minus 1. Now, according to the test, if this limit is not 0, then the series sigma an diverges. If the limit is 0, we don't learn anything. The test is inconclusive. How do I take this limit? Somebody help me with taking this limit. I need your help. Very good. Yeah, Matthew suggests that we renormalize. And that means we're going to divide top and bottom by the fastest growing term. So I'm going to divide top and bottom by n squared. Right, that's a good way to do this. You could also use L'Hopital's rule if you wanted, but it's not necessary. So if I divide top and bottom by n squared, this becomes the limit as n goes to infinity of 2 plus 3 over n squared divided by 5 minus 1 over n squared. And then as n goes to infinity, n squared, of course, goes to infinity. So this would be 3 over infinity right here. And this would be 1 over infinity right here, both of which are 0. So this is 2 plus 0 over 5 minus 0, which is 2/5. And 2/5 is not equal to 0. So what can we conclude? Very good. The series diverges. And here's how you write this. And you need. Am I emphasizing this enough? You need to practice writing these things out. You say thus by TFD, the series S equals sigma n from 1 to infinity 2n squared plus 3 over 5n squared minus 1 diverges. Because I did not work directly with the series. You see any capital sigmas anywhere in this work? No. See any partial sums anywhere in this work? No. Nowhere in here am I using the definition of this object or anything directly related to this object. Nowhere in here do I have the definition of convergence for an infinite series or any partial sums or any series at all. What I'm doing is I'm using this theorem called the test for divergence to tell me something about the series. And you gotta connect your logic together, right? Computer programming people will understand this. If you're trying to connect one thing to another thing in a sequence, an algorithm program, you gotta tell the compiler what library you're pulling from. You gotta explain to your reader why this tells you this. And you got to tell your reader what it is you're talking about. You can't just say diverges. What diverges? The sequence AN? Your mom? My dog? No, this series diverges. Why does it diverge? Because the test for divergence says if the limit of the ANs is not 0, then the series sigma AN diverges. Okay, the logic's extremely important here, and I will be grading you on the logic. Please, as you solve these problems, write out good solutions. This is a good solution. Questions on TFE or this example? Oh. So you have a handful of homework problems that can be solved purely using the test for divergence. And anytime you encounter a series, kind of the first thing you should do is run the test for divergence. Sometimes you'll have to write it out if the limit is not immediately clear. Other times you'll be able to see it in your head. And if the test is inconclusive, there's no need to write it out. I want to give you one last warning about this. Sigma n from 0 or wherever to infinity of an is not the same as the limit as n goes to infinity of an. Please never write this. All right, if you have some series and you're trying to work with it, do not tell me that series is equal to the limit of the terms. It's just not true. This thing is a0 plus a1 plus a2 plus a3, on and on and on forever. This thing is the horizontal asymptote of the sequence AN. Totally different animals. Totally different animals. Okay. The next thing I want to talk to you about are geometric series. And this is an important theorem. Your textbook writes geometric series as sigma n from 1 to infinity a times r to the n minus 1. You can also write them as sigma n from 0 to infinity a naught times r to the n. All that matters is that this series is geometric, meaning the sequence inside of it, the thing that's being added up, is a geometric sequence. So this is any series of the form some constant plus that constant times r plus that constant times r squared plus that constant times r cubed, and so on. These will converge if the absolute value of r is strictly less than 1, and will diverge if the absolute value of r is greater than or equal to 1. Moreover, if the absolute value of r is strictly less than 1, then the sum of the series will be, and I'm going to give you a nice general formula here. It's the starting term divided by 1 minus r. The textbook writes many of these things a little bit differently. The way I am giving you these things is the way you should think about them, because the textbook's formula only works in certain cases, and it will lead you wrong if you follow it blindly. If you follow this formula for the sum of a convergent geometric series, you will get every problem right the first time, and you will not lose point on the test. By starting term, I mean the very first term you see when you write the series out long form. Starting term might be a naught, it might be a naught times r, or a naught times r squared, depending on where this index starts and what this power is. This is an important theorem, so I am going to prove it for you. If the absolute value of r is greater than or equal to 1, then by our theorem on geometric sequences, the limit as n goes to infinity of an, and that's this thing in here, is the limit as n goes to infinity of a naught times r to the n is a naught times the limit as n goes to infinity of r to the n. Remember, if this absolute value is greater than 1, then this limit right here, the r to the n limit, is not going to be 0. This piece will either be dne 1 if r is equal to 1, or infinity. All right. If r is less than -1, it will be dne. If r is equal to +1, it will be 1. If r is greater than 1, it will be positive infinity. In particular, in all of those cases, this limit is not 0. Thus, by TFD, the series sigma n from 0 to infinity an, which is our series, sigma n from 0 to infinity a naught r to the n, must diverge. I'll remind you our theorem on geometric sequences. Maybe I'll pull it up in the textbook really quickly. Do I have that here? right here. Right? If r is strictly between -1 and 1, that is, if r is has absolute value less than 1, then the limit of r to the n will be 0. Divergent for all other values. Divergent for all other values. So this limit will only come out to 0 if the absolute value of r is less than 1. Otherwise, it will be something else, specifically not 0. Thus, by the test for divergence, the first theorem we discussed today, the series made up of those terms must diverge. If the absolute value of r is strictly less than 1, then our series S equals sigma n from 0 to infinity a naught times r to the n has partial sums S sub capital N. Let's see, what is the capital N partial sum of this series? Instead of going all the way out to infinity, we just sum up to capital N. So that would be a0 plus a0r plus a0r squared plus the second to last term would be a0r to the n minus 1, and the last term would be a0r to the n. What I'm going to do here is a clever algebra trick to get a nice formula for this partial sum. And that clever algebra trick is to multiply on both sides by 1 minus r. I know it seems like it's coming out of nowhere, but it's a trick, right? It's a trick. The left-hand side I'm going to leave alone, but the right-hand side I'm going to distribute. And you'll see that this cleans up very, very nicely. What I'll do is I'll first distribute through the 1. So it'll be 1 times this whole thing. And then I'll distribute through the minus r. That'll be minus r times this whole thing. When I distribute through the 1, I get a0 plus a0r plus a0r squared plus I just get that thing again. a0r to the n minus 1 plus a0r to the n. Right? Multiplying something by 1 doesn't change it. Now I'm going to multiply each term by minus r, and I'll write the answer down below here. So negative r times a0 is minus a0r, this times this. a0r times negative r is minus a0r squared. Negative r times a0r squared is minus a0r cubed. All the terms would be negative, so I'll write minus dot dot dot. Negative r times a0r to the n minus 1 is minus a0r to the n. And negative r times a0r to the n is minus a0r to the n plus 1. And you see what's happening here. This and this will cancel. This and this will cancel. This guy, you don't immediately see the guy who cancels with him, but it's the first term hiding in the dot dot dots here. This guy will cancel with the last term hiding in the dot dot dots here. So you can sort of pair these up. This and this cancel. This and this cancel. This guy cancels with something in here. This guy cancels with something in here. This guy and this guy cancel. It's quite beautiful. And what's left is A0 minus A0 r to the capital N plus 1. In other words, i.e. 1 minus r times the capital Nth partial sum is equal to A0 minus A0 times r to the N plus 1. And if I divide both sides by 1 minus r, I get Sn equals A0 minus A0 r to the N plus 1 divided by 1 minus r. Not much left to do from here. I can write this as A0 minus A0 times r to the N times r, all divided by 1 minus r. So the full infinite series S is by definition the limit as capital N goes to infinity of Sn and Sn we just found is this expression above, A0 minus A0 r to the N times r divided by 1 minus r. And the only place a capital N shows up anywhere in this expression is right here, r to the N. And remember, we are assuming that r has absolute value less than 1, which by our theorem on geometric sequences means that limit is 0. So this is going to be, right, this piece right here goes to 0. So altogether we get A0 divided by 1 minus r. And that, ladies and gentlemen, is the theorem. Period. Tombstone. The full infinite series S is going to come out to A0, the starting term, divided by 1 minus r, as long as the absolute value of r is less than 1. That's the reason this piece goes to 0. That's our theorem on geometric sequences from last week. You're not responsible for the proof, but you are responsible for using the theorem. This formula for the nth partial sum of a geometric series, it is a beautiful thing. It's got uses in statistics and chemistry, physics, other places. So if you intend to learn a lot in any of those directions, you might want to stash this somewhere nice. But really what you guys need to be able to do is, for this class, use the theorem. And what the theorem said was, you have a geometric series, it will converge if and only if the common ratio has absolute value less than 1. And in that case, the value of the series will be the starting term over 1 minus r. So let's try an example. Let's investigate the series S equals sigma n from 0 to infinity 2 times 3 to the n plus 1 times 4 to the negative. So that's multiplication. This might not look like a geometric series, but it is. What makes a geometric series geometric is that it can be, that the thing inside is a geometric sequence. It can be written in that form, one constant times another constant to the n. So we need to do some algebra in here. Sigma n from 0 to infinity 2 times. Let's start with the 3 to the n plus 1. 3 to the n plus 1 is 3 times 3 to the n. And then 4 to the negative n, that's the same as 1 over 4 to the n. So this is the same as sigma n from 0 to infinity, 2 times 3. There's no n's in those guys. 2 times 3 is 6 times. And I've got 3 to the n over 4 to the n. Okay, starting to look more like a geometric series. That's 6 times, well, 3 to the n over 4 to the n is 3/4 to the n. And I'll go ahead and annotate here with the algebra rules I'm using. This first move here is just that, like, a to the n plus n is the same as a to the n times a to the n. That allowed me to write 3 to the n plus 1 as 3 to the 1 times 3 to the n. And then here I have this, I have another rule that says, like, a to the n over b to the n is the same as a over b to the n. So all very, very basic algebra rules. It can be hard to remember them in the context of these more complicated calculus problems, but we must. So before I get on to the application of the theorem, any questions about the algebra I did to go from the original statement of the series here to this thing down here? Going once, going twice. Okay. Well, now this is definitely a geometric series, right? This is sigma, some constant, times some other constant to the n. That's the definition of a geometric series. So this is a geometric series with r equal to 3/4. And my theorem says if the absolute value of r is less than 1, so the absolute value of r is the absolute value of 3/4 is 3/4, which is less than 1, which means the series converges. Moreover, the sum of the series, geometric series are part of this rare breed of series where you can tell me not just that the series converges or diverges, but if it converges, you can find the sum. Is S equals the starting term divided by 1 minus the common ratio. Okay, so I need to know what my starting term is. If I write this out, this is 6 times 3/4 to the 0 plus 6 times 3/4 to the 1 plus 6 times 3/4 to the 2, and so on. So that first term is just 6. 6 times 3/4 plus 6 times 9/16, and so on. So my starting term is 6. And my common ratio R was 3/4. This is 1 minus 3/4 downstairs. And we have the power to make that prettier. I'll just copy it down here. S equals 6 divided by 1 minus 3/4. If I multiply top and bottom by the number 4, I can do that. Always multiply a fraction top and bottom by some number. The top will become 24, and the bottom will be 4 minus 3. All right, you got to distribute the 4. 4 minus 3 is 1. This is just 24. This series adds up to 24. What we're doing here is the same thing we did with the series 1/2 to the n on Monday. We just found a more general version of that formula. We found a formula that always works for geometric series. Very, very cool. And if you like, I can verify this for you in Desmos. Before I jump off to that, again, this purple stuff here, this is a good solution. A good solution would have all of this stuff. And specifically, the stuff down here we need to be very careful with. So are there any questions on the purple? Or why all of the purple is necessary, or where any of it came from, anything like that? I'm choosing to multiply by 4/4. It's a good question, right? So what I want to do is simplify this thing. This is kind of ugly, right? It's like 6 divided by 1 minus some fraction. This is a trick to clean up fractions that look like this. So because the denominator of the little fraction downstairs is 4, I know I can clean this up by multiplying top and bottom by 4. So multiplying by 4/4 won't change the value. That's always allowed. And when I distribute the 4 downstairs, 4 times 1 will give me 4. 4 times 3/4 will give me 3. So it's a nice way to turn the denominator into a whole number without messing things up. You could also have a common denominator. I could write this as 4/4 minus 3/4. So that would be 6 divided by minus 3/4, 1/4, and then flip and multiply. And that would get you here also. But I like this because I think it's fast and easy and clean. So just trying to simplify this. And multiplying by 4/4 is a nice trick to simplify this. So it's good. I really do want to hear what you're thinking, even if it's just like, what the fuck, or where did that step come from? Those are precisely what I want to hear. Any other thoughts or feelings on this? Okay, let's try one more. Here, I'll highlight why the book's formula is not ideal and why you should use the one I give you instead. Let's investigate the series S equals sigma n from 3 to infinity 5 over e to the n. E here being Euler's number, 2.71828, blah, 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 blah. The series is geometric. The series is geometric. So here I can write S as sigma n from 3 to infinity. The 5 upstairs is the same as having a 5 right here. And then I've got 1 over e to the n. And then 1 over something to the n is the same as 1 over that thing, all in parentheses, to the n. Because 1 to the n is 1. So once I write it in this form, sigma, some constant times some other constant to the n, we see that this is a geometric series with r equal to 1 over e. So the absolute value of r is the absolute value of 1 over e, which is 1 over e, and that's less than 1. Why? How do I know 1 over e is smaller than 1? Anybody? Because e is like 2.718. Is bigger than 1. Yeah, thank you. Yes, exactly. So the reciprocal of a number is going to be smaller than 1 if and only if that number itself is bigger than 1. All right. Thus, by our theorem on geometric series, this series S equals sigma n from 3 to infinity 5 times 1 over e to the n converges. Moreover, the sum of the series is S equals. Now here's where if you use the a over 1 minus r formula that you'll find in the book and in so many places online, you get boned. You take the starting term and divide by 1 minus r and you're Gucci. The whole a over 1 minus r thing only works if your series starts at 0. Here, what is the starting term? This is, if you take the first term here, that's the term you get with n equal to 3. That's 5 over e cubed. The next term would be 5 over e to the 4. The next term is 5 over e to the 5, and 5 over e to the 6, and so on. So you see the numerator here is not going to be 5. It's going to be 5 over e cubed. We have to divide this by 1 minus r. R is 1 over e. this is the sum of that series. Again, this is kind of an ugly expression. I could multiply top and bottom by e. That would help a little bit. I could multiply top and bottom by e cubed to try and get rid of the fraction upstairs. Many options as to how to clean this up, just to get a variety of algebra tricks under our belt. Also, this is 5 over e cubed times 1 over 1 minus 1 over e. And I'll distribute the e cubed downstairs. Applying straight across, that's 5 over e cubed minus e cubed times 1 over e is e squared. I think that's about as pretty as you're going to get them. And again, the whole purple is necessary to have a good solution here. If you omit any of this, then we're not at a complete solution. What I mean by that is, if this were a test question and you skip any of the purple stuff, I wouldn't be able to give you a grade. This will be our last example of geometric series. Questions on this guy? Okay. There is a theorem in the book that I think everybody would use implicitly if I didn't show it to you, but I'd be a bad enough teacher if I didn't show it to you. These are the rules for the sigma operator. Sigma algebra rules. I'm not going to write the bounds here. Could be from 0 to infinity, could be from 5 to infinity. Yeah, let me come back here for a second. So rules for these sigma operators, algebra things. So if sigma an and sigma bn both are convergent series, and it's understood here that these guys start at the same value and go up to infinity, and C is a constant, then sigma of C times an, constant inside, just like with an integral, constant multiples can top out. So that's C times sigma of an. Right, you can put in the n from 0 to infinity or n from 1 to infinity if you want, as long as you use the same thing everywhere. But the idea is it doesn't matter what the starting value is. Sigma of an plus bn. Again, just like an integral, you can split it up over addition. This would be sigma an plus sigma bn. And again, just like with an integral, sigma of an minus bn will be the same as sigma an minus sigma bn. but I'm assuming here that both sigma an and sigma bn are convergent series. So kind of in this same space, I want to discuss rules for adding and subtracting convergent and divergent series. And I'm going to give this to you in a shorthand because it's just so much easier to do it. If I take a convergent series and I add it to another convergent series, what do you think the result would be? Okay, sigma an and sigma bn are both convergent. What do you think I get when I add those up? A convergent series, a divergent series? We don't know. And the answer is another convergent series. If I take a convergent series and I add it to a divergent series, what do you think we'll get? Show me with me. Show me we're listening. Hold call if I have to. No. So if I take a convergent series and I add it to a divergent series, I will get another divergent series. If you take something finite and you add it to something infinite, you're guaranteed to get something infinite. The fun one is if you add two divergent series. If you add a divergent series to a divergent series, this could go either way. Now, based on the lack of responses there, I'm worried that I'm losing you guys. Anybody still with me? Anybody still watching or listening? That's good. Yes, this should all feel new. That's okay. This definitely is all new. Okay, thank you for the engagement. Okay. I want to, for a second, talk about how this is possible. How could a divergent series plus a divergent series be anything other than divergent? Well, imagine you have some divergent series and you add to that the negative version of that same series. Then when you put those together, every term is going to cancel perfectly, and you're just going to get 0. So it is possible for the sum of two divergent series to come together to a convergent series. And this is not at all obvious. And what this this means is that you need to be careful when you go splitting up series like this or combining series using these rules. What these rules say is that you can do the same thing with series as you can do with integrals. You can pop out constants, you can split them up over addition, and you can split them up over subtraction. And as long as everybody is convergent, then all the series up here will be convergent, including the combined or the split up versions. But if the two series on the right-hand side are divergent, like here, if AN and sigma AN and sigma BN are both divergent, it's possible that this guy is convergent. So you can get into some trouble if you're not careful. You don't always want to split up series. It's not always a great idea. And I'm going to show you in the last few minutes here some examples of series where we're going to apply a trick called telescoping series trick to collapse the partial sums down into nice expressions. And these will be examples where if you were to take the series and split them up, you might not end up getting convergent series out on the right-hand side, even though the left-hand side is. So the last topic for today is telescoping series. And you have several of these in your homework. A telescoping series is a series where the terms cancel. In which many and most of the terms cancel with other terms in the series. The way we handle these is we write out the partial sum S of capital N, simplify, and then get the full infinite series S as the limit, right? Just using the definition, limit capital N to infinity of S of capital N. These are the last series we're going to encounter in section 11.2. There is some 11.3 stuff in your homework this week. Unfortunately, because we missed on Wednesday, I cannot get to all of that. So I will be extending that portion of the homework. I'll either move those problems into a new problem set or give you a little extra time on that problem set. But we do need to talk about telescoping series. And because these are such a general thing, but it's not like a simple formula, the only way I can really describe this is through examples. So we're going to start by investigating the series S equals sigma n from 2 to infinity natural log of n over n plus 1. I claim that this is a series where most of the terms cancel and go away, which makes it a remarkably easy series to work with, but only if you approach it from this angle. Now, at the start of class, I said, first thing you should do when somebody hands you a series is run the test for divergence. You should always ask yourself, does the test for divergence show me this series diverges? Because if it does, that's an easy test. You just stop there. I'm going to start by running TFD. TFD says if the limit as n little n goes to infinity of a little n is not 0, then the series diverges. So the ANs in this series are the natural log of n over n plus 1. What does n over n plus 1 do as n goes to infinity? Kind of forget about the natural log for a minute. What does this inside do as n gets big? That's 11.1 stuff. Who can help me with that? You guys know this. I know you know this. Cover up the natural log. Yeah, if I cover up the natural log, n over n plus 1 goes to 1. So this limit is the natural log of 1, which is 0. So what do I get from TFD? If the limit of the ANs is equal to 0, what does the test for divergence tell me? Does the series diverge? Does the series converge? Or do I learn nothing? Good. This is inconclusive. Which means TFD, the test we're running, is inconclusive. Okay. Well, that's not going to work. So we better try something else. This series is definitely not geometric. This is not some constant raised to the n inside here, right? There's no way to write this as r to the n. So I can't use anything about geometric series. I sure as shit hope it's telescoping then, because that's the only other thing we've talked about. Also, this is we're talking about telescoping series right now. So what we're going to do instead is we're going to use some algebra the natural log of n over n plus 1 is the natural log of n minus the natural log of n plus 1. And anytime you see a series where the things you're adding up look like they could cancel from term to term, right? Like natural log of some number minus natural log of that number plus 1. If you add up a bunch of terms like that, you're going to have a bunch of positive natural log things and a bunch of negative natural log things. And there's a very good chance that they will cancel. So now we're going to write out the partial sum. If I plug in 2 for n here, I get the natural log of 2 minus the natural log of 3. If I plug in 3 for n, the next term of this series would be the natural log of 3 minus the natural log of 4. If I plug in 4 for this series, I get the natural log of 4 minus the natural log of 5. Plus dot, dot, dot. This is the nth partial sum though, so this series doesn't go on forever. It has a few terms at the end and then it stops. If I take little n to be capital N minus 1, the second to last term in the partial sum is the natural log of capital N minus 1 minus the natural log of capital N. And the last term in this partial sum is the natural log of capital N minus the natural log of capital N plus 1. That is the capital N partial sum. And if you look here, you have a negative natural log of 3 plus natural log of 3. Negative natural log of 4 plus natural log of 4. Where else is there cancellation? Negative natural log of n plus natural log of n. This was the n equals 2 term. This is the n equals 3 term. This is the n equals 4 term. This is the little n equals cap n minus 1 term. This is the little n equals capital N term. What you see here is that we really have just written out the capital N partial sum. And we see a shitload of these terms cancel. The question is, what remains? What about this natural log of 5? Do you think he's going to live or die? Is there a term hiding in these dot dot dots with a plus ln 5? He's going to die. Good. The very next term in these dot dot dots is plus ln 5 minus ln 6. He's going to be eaten up by the very next term in here. He's gone. See you, brother. Same thing with this guy. The term right before this in the dot dot dots is natural log n minus 2 minus natural log n minus 1. He is going to die. He's going to be killed by the term immediately before that. So what's going to survive overall here? The very first term, ln of 2, and the very last term, minus ln of capital N plus 1. When I say we're going to write out and then simplify the capital N partial sum, this is what I mean. We're going to get a formula for Sn with no dot dot dots in it. That's what we've got here. This process of all the cancellation should remind you, and is where the name comes from, of those pirate telescopes. Think like Johnny Depp in Pirates of the Caribbean. He's like looking out, looking out, looking out, and he sees something. And then when he goes to put his telescope away, what does he do? He goes and collapses the whole telescope. That's what's going on with this series. The partial sum here, like the very tail piece, the very front piece and the very back piece are left, but everything else in the middle collapses. All of the terms in the middle collapse, and you're just left with these. So TFD was inconclusive. TFD didn't do the job. But treating it as a telescoping series, we're able to get a nice formula for Sn. So now we can say S, the full infinite series, by definition is the limit as capital N goes to infinity of S sub n is the limit as capital N goes to infinity of natural log of 2 minus the natural log of capital N plus 1. And as capital N goes to infinity, what does the natural log of capital N plus 1 do? What does this piece do? This piece, ln2 is a constant. I don't care about him. What does this do as the inside gets bigger and bigger and bigger and bigger? The natural log function, as its inside goes to infinity, the whole thing goes to infinity. So this is ln2 minus infinity, which is negative infinity, plus a series S diverges. Because series converges means that the limit of the partial sums exists and is finite. Here, the limit of the partial sums is negative infinity, that is not finite. So this is a divergent series. That's it. This is kind of the simplest of all possible telescoping series. And before I let you go, I want to show you one more example. We won't have time to run all the way through it, but I want to show you so you have a little bit of exposure to this other way that telescoping series can come about. People ask me, how can I tell if a series is going to telescope? There's no general rule. You can try writing out a few partial sums and see if there's a lot of cancellation. If you started doing that with this in its original form, you wouldn't have seen them. You wouldn't have seen the cancellation. You'd have like ln2 over ln3 plus ln3 over ln4 plus ln4 over ln5. If you write it out like this, then you'll see it. The other kind of common trick, we do have to move a little quick here, I'm sorry, is if your series sum from 2 to infinity again, say 6 over n squared minus 1. If the thing inside your series looks like something you could do partial fractions on. So here's 6 over n squared plus 1. That's ripe for some partial fractions. And after you do the PFD, you'll see that you can write out the partial sums and get a lot of cancellation. Here's what we're going to say. 6 over n squared minus 1 is 6 over n minus 1 times n plus 1. And this is sigma n from 2 to infinity, 6 over n minus 1 times n plus 1. And if I set this up using partial fractions, I'll write a over n minus 1 plus b over n plus 1. Through the normal PFD stuff, 6 equals a times n plus 1 plus b times n minus 1. If you evaluate this at n equals 1, you'll get 6 equals 2a, which means a is 3. And if you evaluate this at n equals negative 1, you get 6 equals negative 2b, which tells you that b is negative 3. So our series S can be written as sigma n from 2 to infinity 3 over n minus 1 plus 3 over n plus 1. And this guy has partial sums, Sn equals, we'll write out a few terms. So it'll be the sum from 2 to n. So the little n equals 2 term is 3 over 2 minus 1 is 1. Oh, sorry, this is minus here. Minus, this 3 is a negative. Minus 3 over 2 plus 1 is minus 3 over 3. And don't simplify, right? When you do this, don't simplify. You'll make life harder if you do. When I plug in little n equals 3, this is 3 over 3 minus 1 is 3 halves. Minus 3 over 3 plus 1 is 3/4. When I plug in little n equals 4, I get 3 over 3 minus 3 over 5. The third from last term, the little n equals capital N minus 3, will be 3 over capital N minus 4 minus 3 over capital N minus 2. The second to last term, little n equals capital N minus 1 term. Sorry, this would be little n index these. Never a bad idea to index these. So this is little n equals 2, little n equals 3, and little n equals 4. This was little n equals capital N minus 3, little n equals capital N minus 2. Okay. Would be 3 over capital N minus 3 minus 3 over capital N, let's see, little n minus 2 plus 1 is 3n minus 1 plus, I've got a couple other terms I'm going to put in here, plus two terms. When little n is capital N minus 1, this would be 3 over cap n minus 2 minus 3 over cap n plus, when little n is equal to cap n, 3 over cap n minus 1 minus 3 over cap n plus 1. Minus 1 and little n is n. So this is your nth partial sum. We want to look for cancellation, just like we found in the last problem. The pattern here is a little bit different. Here, the negative guy from a given term cancels with the positive guy, not in the next, but 2 terms later. So this fellow cancels with this fellow. If you look here, the negative guy from this term cancels with the positive guy 2 terms later. This fellow cancels with this fellow. The negative guy from a given term cancels with the positive guy 2 terms later. This fellow cancels with this fellow. There is no negative guy 2 terms before this. There is no negative guy 2 terms before this. So both the 3 halves and the 3 over 1 will survive. The 3 over 5 here will cancel with the positive guy 2 terms later in there. Similarly, the 3 over n minus 4 will cancel with the negative guy 2 terms before in there. And this fellow will also cancel with the guy, the negative part in the last term in those dot dot dots. So practicing finding this cancellation pattern is an important thing for telescoping series, and you won't get it unless you practice it. When we simplify, I have left 3 over 1, which is 3. I'll write it as 3 over 1, plus 3 over 2. Oh, I didn't write it. So what about this 3 over 4? Does he live or die? Well, what is the very next term in here? It would be plus 3/4 minus 3/6. So he will cancel with the very first term hiding in the dot dots. So this term and this term will survive. This term and this term will survive. That is your nice formula for Sn. So now we're done. Now we can say thus, S is the limit as capital N goes to infinity of S of capital N, which is the limit as capital N goes to infinity of 3 plus 3 halves minus 3 over n minus 1 minus 3 over n plus 1. And these two terms go to 0. So we get 3 plus 3 halves. 9 halves. In other words, the series S converges to, oops, sorry, 9 halves. 9. So I know I ate up a little bit more of your time here at the end. These examples of telescoping series, they're important, but I wanted to make sure that you saw at least one where we do the partial fractions. Fabrice, I got your message. Believe me, buddy, I'm on it. Anything you guys would like to ask about this example before we part here today? Yeah, finding the cancellation patterns in partial sums is a little bit tricky. It is. It can be helpful, I think, sometimes, instead of trying to go straight to the nth partial sum, to write out like 3 or 4 regular partial sums, like the first, second, third, fourth partial sum. Once you see the pattern in there, try to go for the full nth partial sum. But the long-term goal is always to get a nice formula for Sn. If you look in Canvas under the modules, there are several links to Patrick JMT videos where he does this, right? Just like I'm saying, he finds the formula for the nth partial sum by thinking about the first few partial sums and looking for a pattern. That's a perfectly valid way to do things. Any other questions or comments on this? Alrighty then, I'll go ahead and end it here. Your homework, I'm going to yank out the 11.3 problems. So everything from 11.2, I still need you guys to do and have that done by Monday. Next week, we will start 11.3 because we lost a day this week. We weren't able to get there. That's okay. But please make sure you finish the 11.2 problems. Don't worry about anything related to the integral test. And we will talk about 11.3, which is the integral test, on Monday of next week. Oh, the test, the exam. Exam 2. I have to think about a little bit, but I think we're probably going to end up pushing that past spring break, which isn't ideal. I really like to get exam 2 done. Oh no, we planned on doing this after spring break anyway. All right, doesn't even matter for you guys. You're Gucci. Exam 2 will be after spring break anyway. Okay, that's it for me then. I will see you guys on Monday. Take care.